Okay, so this video is empirical and molecular formulas, and we're going to be looking at, in Unit 2, Interpreting Formulas, we're looking at maternity page 115. And so let's just start with what we know already about empirical and molecular formulas, which is at least the name. So we know that that word empirical means lab. And so this is going to be data from a lab that we're going to use, and we can use it to determine the formula. It's based on the idea of percent composition. So if we know that a compound has, 50% nitrogen and 50% oxygen, we can use that information to then find its empirical formula, and then from its empirical formula find its molecular formula. So our state standard is SC.912.P.8.9 because we're interpreting formulas. And we have 4 questions. How is a molecular formula different from an empirical formula? How do you find the empirical formula? How do you find the molecular formula? And what do you do if you have an unusual ratio? Okay, so let's start with just defining molecular and empirical formulas. And so I'm going to start with empirical because that's what we're going to get from our lab data. So an empirical formula is the simplest ratio. Simplest ratio of elements. And so it's going to be based on the mole. So using the percentages, we can determine grams, and then using our information from the periodic table, we can take that those ratios and write the simplest ratio of elements to form the compound. That's the empirical formula. The molecular formula, on the other hand, is the true formula. The molecular formula is the true formula of the compound. And we can take that empirical formula that we got from our lab data and we can use it to find the molecular formula or the true formula of the compound. So for example, we may find something that says C2H4O3, and that would be empirical formula. If I knew the ratio between empirical and molecular formulas, which is what we'll be calculating, I might see that the molecular formula for that would be C4H8O6. And you can see that they're related to each other by a factor of 2. 2 times 2 is 4, 4 times 2 is 8, and 3 times 2 is 6. So they'd be related to each other by a factor of 2, and we're going to learn how to calculate that in our video today. So let's just start with finding this empirical formula, or finding the simplest ratio of elements. The material that you're going to see is usually going to give you percentages, or they may give you grams, but often it's percentages because that's what they're going to find from their lab calculations. So we're going to turn the percentage sign into a gram sign, and then we're going to do a mole conversion to figure out how many moles. So that's step 1, get it to moles. Step 2, once we have each of our elements in moles, then we're going to divide all of those answers by the smallest mole answer that we have. Once we have turned everybody into moles, and we have divided by the smallest, then we are going to round to the nearest whole number. The only difference would be if you got an answer after you divided that said 0.5 or said 0.3, then we're going to have to do something different. That's what we call an unusual ratio. Okay, so let's just kind of go through here. So the first thing we've got to do is we've got to get to moles. Once we get to moles, we're going to divide by the smallest mole. Then we are going to round to the nearest whole number, but we're going to pay attention to our exceptions of 0.5 and 0.3. And then once we have done all of those things, then we are going to write our formula. And so let me show you what I mean by that. So let's look at this. It says find the empirical formula if 40.1% of a sample is sulfur and 59.9% of a sample is oxygen. Okay, so we start by just taking that percentage sign and turning it into a gram sign because we're assuming a 100-gram sample. So we have 40.1 grams of sulfur, and we are going to have 59.9 grams of oxygen. Okay, we're going to turn each of those into moles. So we're just going to use their mass on the periodic table and say grams of sulfur in 1 mole. And we know that sulfur has a mass of 32.066 on the periodic table. And oxygen has a mass of 15.999 grams on the periodic table. So we're going to get both of those answers. So let me grab my calculator. And I'm going to be able to see that 40.1 times 1 divided by 32.066 is going to give me 1.251. It's important that I always go 3 places after the decimal because we want to make sure that we are looking at the same types of values. So I'm going to round to 3 places after the decimal. And then for my second value, 59.9 divided by 15.999 gives me 3.744. Okay, so I've done my first step. I've turned my percentage signs into gram signs just by changing the sign, and then I've converted them into moles. Now I'm going to divide each of them by the smallest, and so 1.251 and 3.754, this is definitely the smallest. So I'm going to divide both of them by the smallest, and I'm going to get an answer. So I'm going to take 1.251 divided by 1.251, it's going to give me 1. And then 3.744 divided by 1.251 gives me 0.267. Now normally what we would do is we would round this, let me check that one more time, that doesn't look right. 3.744 divided by 1.251. Okay, there we go. That looks much better. 2.992. That is very close to 3. So we're going to round that to the nearest whole number of 3. I noticed that neither of my answers had ended in 0.5 or 0.3. Okay, so these then are my ratio numbers. It means that I have 1 S for every 3 O's. So my empirical formula is just going to be S 1 time and O 3 times. And so that's my empirical formula. I also need to just know its mass because that's going to be important for us in the next step. So we're going to go ahead and do that. So I know that oxygen is 15.999 times 3 plus sulfur, which is 32.066, and it gives me a mass of 80.063 grams. And so that is my first step on how to find empirical formula. So remember, if they say empirical formula, their percent sign is going to be changed to gram. We take each of those percentages and we turn them into moles. We divide by the smallest of our values, which in this case was 1.251. And then once we've divided by those, we round to the nearest whole number, checking if we get a 0.5 or a 0.3, which we didn't. And so then we take those whole numbers and we use them to write the ratio 1S to every 3 O's. And then we got the mass of that on the periodic table. And so that's our first step on how do we find empirical formula. Okay, now we're going to take it a step farther and we're going to take this information to find the molecular formula. Okay, so when we find the molecular formula, the very first thing we have to do is start with the empirical formula, which means that a lot of times we're going to have to actually go in and do all the math we just did. But once we have done that, it's pretty easy because all we're going to do is divide the molecular mass, which you'll notice here is given to you in the problem, by the empirical mass, which is what we just added up from the periodic table. So that's pretty important. The molecular mass is given from the problem, and we're going to have to add up the empirical mass from the periodic table. Once we have done both of those things, then we're going to round that answer to the nearest whole, and then we're going to use that whole number to multiply each subscript, because it's our ratio. So we're going to actually have to do all of the work for this one, but it's going to, help us out. So find the molecular formula. That means I'm going to have to go from empirical, divide the molecular by the empirical, round to the nearest whole, multiply the subscripts. If we have 40.1% sulfur and 59.9% oxygen, and the molecular mass is 160.15 grams per mole. Okay, we obviously have just done this problem, but for sake of practice, I'm just going to do it again. So 40.1 grams of sulfur, because remember the percent signs become gram signs. The mass of sulfur on the periodic table gives us 1.251. I need to do the same thing for oxygen, so 59.9 grams of oxygen its mass on the periodic table is 15.999 grams of oxygen in 1 mole. That gave me 3.744. Of the two, I picked the smallest, divided each of them by the smallest, used this to get my empirical formula. So my empirical formula was SO3, and its mass, once we did oxygen times 3 and then sulfur, was 80.063. Okay, so in order to find the molecular formula, I've got to take the molecular mass given in the problem divided by the empirical mass. So molecular divided by empirical. Well, the molecular mass given in the problem was 160.15 grams per mole, and the empirical mass that we got was 80.063. And so when you divide those, you're going to get something really close to 3. I'm sorry, really close to 2. 160.15 divided by 80.063, and we get 2.00002. So we know that that's going to be 2. So this is our multiplier, 2 times. That means our formula of SO3 has to be multiplied 2 times. And so when I go in to do that, I take S times 2, which would be S2, and O3 times 2, which would be O6, and this would be my molecular formula. So I found my empirical formula. I took the molecular mass given in the problem, which was 160, divided by the empirical mass once I took my formula that I had derived and got its mass from the periodic table. I divided those and rounded to the nearest whole, which was 2. And then I take that 2 and I multiply it into my existing empirical formula. And so that gave me S2O3. And that's finding molecular formula from empirical formula. So just to recap what we've talked about today, we know that the empirical formula is the simplest ratio of elements, and that's going to be from lab data when they're analyzing the composition of a compound. And then we can take that empirical formula, since it's in the simplest ratio, and once we find the relationship between empirical and molecular, which is the number we just found, we can multiply it in. So in this case, C2 became C4, H4 became H8, and O3 became O6. To find the empirical formula, any percentage signs automatically become gram signs. If it's already in grams, awesome. But if not, just make the percent sign a gram sign, turn it into moles by dividing by their mass on the periodic table. Once you get your 2 answers, divide by this, or 3 or 4, however many, divide by whatever the smallest is. Get your ratios, rounded to the nearest whole number. Watch out for things that are 0.5 and 0.3. If you end up with something that is a 0.5, you would have to go in and multiply everybody by 2. So I'm just going to do like a little pretend for a second once I finish talking through this to show you what that would look like. Then we're going to write the formula and find the mass. Okay, so let's just kind of pretend that we've got a different situation. So let's say divided by 338. Okay, let me write this down so that I can get this done correctly for you. 3.382 times 8.84. Okay, so let's say that when we had done our 2 answers, we had divided, I don't know, let's just say this is x, we divided by x on the periodic table. This was y, we divided by y on the periodic table. Okay, and so once we had finished that, we had 8.455 and we had 3.382. Now, these are just completely made up numbers. Okay, so this would be the smallest. I would divide it by 3.382, divide this by 3.382. Okay, well, this is going to give me 1. But when I put in my calculator 8.455 divided by 3.382, I get 2.5. Well, that's one of my exceptions. If once I divide, if I am not near a whole number, and if I am near a 0.5, then I've got to go in and multiply everybody by 2. So since I have this 0.5 issue, I would say times 2 times 2. And that would give me 5 and 2. And so my formula would be x5, Y2 in this situation. So I just wanted to show you that, but that's after I have divided by the smallest. If I end up with a 0.5 situation, which is one of our exceptions, you multiply by 2. After you've divided by the smallest, if you have a value that ends with 0.3, then you would multiply everybody there by 3. Okay, so that's empirical formula. Molecular formula, when we take that molecular mass given in the problem divided by the empirical mass, either they'll give us the formula and we find the empirical mass, or they give us the information to find the empirical formula, which then allows us to give us the empirical mass. That gives us a whole number. When we divide those two values, once we've divided the whole two values, we plug them back into the problem, and so SO3 became S2O3. All right, hopefully that helps you with empirical and molecular formula. Let's get started on your work.